Hi, good morning, everyone. Good afternoon and good evening. Something that I haven't realized until I was told yesterday is that this week is actually a reading week at York University, which is my institution, and also reading week at University of Toronto. Actually, I was not supposed to be teaching this week. Now it's too late to fix that, I guess. So I just go on, but I guess that some of you may be watching this on the video and being fairly annoyed at me for actually teaching this week. Well, anyway, so I didn't cancel. I mean, nobody mentioned it to me until now, and although it was my job, I guess, to check the calendar, I didn't, and so here we are. So anyway, in case you are watching this on video and you missed 2 classes, the previous class wasn't such a big deal. Today's class is quite important. If you feel that you need to catch up, I'll be happy to help with that. And well, okay, so I guess since you showed up, let's go, and we'll see on Monday how it goes. So I reserve the right to cover some of this material again on Monday in case I am attacked by a mob of angry students who were on reading week and who didn't expect me to do what I'm doing right now. Anyway, so let's go ahead. So today we are starting, well, probably the most complicated proof that I'll cover in this course. Proof that if this is not in ZFC, that if ZFC has a model, then it has a model in which all automorphisms of the Calkin algebra are inner. Or another way of saying this is that the statement all automorphisms of the Calkin algebra are inner is relatively consistent with ZFC. Again, there is this logical quirk that we cannot prove that ZFC is consistent unless it is inconsistent, which we don't want to know if that's the case. So I just have to say this every time I'm talking about this. Anyways, so more precisely, what I'm going to do is state a certain axiom, open coloring axiom, and prove that from that axiom, it follows that all automorphisms of the Calkin algebra are inner. I'm not going to prove that this axiom is relatively consistent with LFC, simply because proof doesn't belong to this course. You'll just have to take my word on that or check with some set theorist to convince. I'll say a few words about relative consistency when you come to that. All right, so here is a roadmap for this proof. So phi is some automorphism of the Calkin algebra. Here H is separable. There are things to say in the case when H is non-separable, but they are different. This is really the Calkin algebra, the one that corresponds to a separable Hilbert space. So one important point that I'm actually going to prove later on, but it's just important to properly understand this roadmap. The unit ball of B of H, so that's what this one means. It is a Polish space, namely it's a separable, completely metallizable space with respect to a strong operator topology, and F of E, right? So this is not phenomenology. This Banach subspace of Banach subspace of B of H. It's actually also a weakly closed subspace of B of H, but not a subalgebra. It is also a strongly closed subspace. So it's a closed subspace of B of H. We'll see why it matters. So there are 3 steps. Most of those steps have infinitely many sub-steps. Basically, for every epsilon greater than 0, you have to do a different thing, similar things, but different. First step is that OCAT implies that for every E, which is a partition of natural numbers into finite intervals, there is a strongly continuous function from the unit ball of F of E to unit ball of B of H, which lifts phi. Note, since these are cyst algebras, they are homogeneous. If you know that something happens on the unit ball, you can just scale it up to get it to happen on the entire space. And the reason for just saying unit ball is this sentence here. These are polished spaces. So talking about continuous functions, these are continuous functions between separable, completely metallizable spaces. Right. So that is the first step. So we do it for each E. And you see that there are really Aleph 1 different things one needs to do. You have to do it for each E separately. And for each E, you also do it for each epsilon greater than 0 separately, and somehow put those approximations together. So step 1 is really a lot of work. That's really where the bulk of the proof goes. Second part, which has little to do with set theory, which is proving that once you have function like this, then that function, I mean, this automorphism, it can be implemented as conjugation by a unitary, U sub E. Now, this proof, as I said, it's not set theory by any definition. This is another very interesting subject, so-called Ulam stability of star homomorphisms. We'll come back to that. So this is really theorem from some other course. Now, you see, once you collect these pieces, as in 1 and 2, what you have is this family of pairs. E is element of part, and UE is a unitary. And those unitaries cohere on different E's. So if E is below F in that ordering we defined before, then UF and UE implement the same automorphism, namely phi, on this FE. So we have what I call a coherent family of unitaries. And again, by using OCAT once again, we will prove that this family can be uniformized. Namely, we can find a single unitary V, which implements restriction of phi to f of E for all E. Now, I'm not sure if I should be saying this, but this is my favorite part of the proof, really. And if any of this is a proof from the book, then it's this one here. Also, note that this is really the part that we know is independent from ZFC. We just constructed from continuum hypothesis a coherent family of unitaries. I didn't call it that, but it was coherent family of unitaries, which was non-trivial, which implemented an outer automorphism of the Calkin algebra. Actually, two Aleph 1 such automorphisms. So you see what, once we prove this, what this will imply is that if you assume this other axiom OCA, then then no automorphism of that form can be outer. Now, that's not enough for the theorem. Of course, we have to prove that every automorphism is of that form, and that's for that I can promise only blood, sweat, and tears. That proof is, I'll go slowly, but it's not a nice proof, which probably means that we don't have the right proof. I hope that somebody comes up with the right proof one day. Okay, so if there are no questions, I should probably open the chat window. If there are no questions, let's go on. So I'll start by introducing some notation from Ramsey theory. So we're talking about partitions of pairs. For any set X, this notation X in square brackets squared stands for the set of all unordered pairs of all unordered pairs of elements of X. Right, so it's the family of all two-element subsets of X. Now, the right way to think about it is really to think about X squared, right? So this is X, this is X. Look at, actually, okay, this is X. This is not X squared. This is X squared. This is another copy of X. Remove diagonal, and then just identify points which are on the opposite square side of the diagonal. So you can really think of this x squared as the upper triangle here, all pairs of elements x, y, which are above the diagonal. Now, to have some meaning for above the diagonal, you need to have some linear ordering on x, and we'll have that linear ordering in many cases. But anyway, this is the picture. And now I'm going to state two theorems that we are not going to need. The reason is that I just want to set up basically notation and situation, not notation, to basically introduce situation to make sense out of the axiom that I'm going to state, because I really think that knowing these two results gives you the right background for appreciating the axiom that I'm going to state. So, okay, so once again, if you need to take a nap, you can take it right now. But I do think that you lose something. Technically, you don't lose anything, but in some deeper way, you lose context. So here is first Ramsay's theorem. There is Ramsey theory. So this is a theorem which started entire lively subject of mathematics. This is its easiest form. For every partition of unordered pairs of natural numbers into two pieces, right? So this square bracket square, this means that it's disjoint union. Right? So I'm just covering this set of pairs in two pieces. There is an infinite subset of natural numbers, so that all pairs of elements in that subset either belong to one piece of the partition or they belong to the other piece of the partition. So you may have seen, I mean, if you're a set theorist, you probably saw this theorem. Set theorists love this theorem. If you worked in Banach spaces, again, you must have seen this Banach space. People love this theorem. Operator algebraists don't seem to have much use for Ramsey's theorem for some reason. But anyway, so this is quite an influential result. Now, let me, again, we don't need it, but I'll just write down notation. You see, there is this Hungarian notation. This theorem is very popular in Hungary. There is this Hungarian notation for this sort of thing. Aleph 0 arrows, Aleph 0 2 2. Now, let me just note what is what. So first, Aleph 0 is really cardinality of the set of natural numbers. The second Aleph 0 is cardinality of this set that you get, which is the same. It's an infinite set. Now there are these two indices. Superscript 2 stands for these two here. Also superscript, you're talking about partitions of pairs. And finally, subscript 2, well, it is the fact that you have two colors. So one can put here some other numbers, and it is very easy to see that this number 2, the green 2 here, can be easily improved to 3 by just basically repeating use of Ramsey's theorem. This upper, the purple 2, can also be increased to 3, 4, and whatnot, but there is some work needed there. But anyways, so as long as you're partitioning countable set and want to get an infinite subset, as long as your partitions are finite, you can do whatever you want, and there is much more really. But now you may get carried away and say, well, what's the difference? What happens later? And here is classical result of Sierpinski. There is a partition of pairs of real numbers into two pieces. Now you may be wondering, why is there square root here, square bracket here, and round here? Just because I wasn't careful, there is no difference really. You could put these are disjoint. So there is partition of pairs of real numbers such that for every uncountable set of real numbers, neither of these two relations happens. So in any uncountable set, you are going to have pairs which belong to both L0 and to L1. So this shows, again, I'll use Hungarian notation, that 2 to Aleph 0 does not arrow Aleph 1 to 2. right? And now you know what the notations stand for, right? So it's 2 to all F0 is cardinality of the reals. You cannot even get uncountable set. So there is, I mean, with some cardinal arithmetic, there can be quite a gap between continuum and LF1 and these two. This result can be improved a lot. Basically, there is the strongest possible result due to Justin Moore in this direction, but we don't need it. We don't need Sierpinski's theorem either. The only reason why I'm stating this is to put the right proper context to the theory, to axiom that I'm going to state in a moment, right? So once again, if you're partitioning countable set, pairs in countable set, you can do whatever you want. You can have all homogeneous sets that you may possibly need. If you have an arbitrary partition of your uncountable set, you may not get homogeneous sets, which are uncountable. So I just use word homogeneous set that's introduced on the next slide. So it's right here. So a set Y such that pairs from Y belong to some set L is called L homogeneous. Okay, and other terminology, and now this is important. So if X is the topological space, we'll be looking at separable metric spaces, but this is more general. Then if you have L subset of pairs in X, we say that it's open if set of all ordered pairs X, Y for X, Y, and L is an open subset of X squared. Namely, what we have is that with X and X like this, if you remove the diagonal, we don't want diagonal. Right? Diagonal is a closed set, so its complement is open. Our L, you can think of it as sitting above the diagonal, but you can just duplicate all points from L. So maybe I should make some effort to make this L look so that it's clear that I'm copying it. I guess this looks some sort of amoeba or something. Actually, amoeba means something in set theory. All right, so this is our set L. We just identify these pairs in L with both of these, and this set is open. Right. So yeah. So this is definition. And now we say that partition is open if L0 is open. So this is asymmetric. It's very important that the axiom that we'll be looking at is an asymmetric axiom. So that there is difference between L0 and L1. If you swap them, you get different meaning. Right, so L0 is open, which means that L1 is with appropriate definition closed. Except that diagonal is not there. So it's closed subset of an open set, but so L0 is open. That's what really matters. Now, okay, so here is our axiom OCAT. I should say there is a long and rather annoying story about the history of this axiom. I'm just going to gloss it over. I'll just call it OCA. There is more than one axiom with this name, and it doesn't really matter from a mathematical point of view, so let's not worry about that. Let's just call it OCA and go. And here's the axiom. Whenever X is a separable metallizable space, and we have a partition of unordered pairs of X in two colors, I hope that you're not annoyed by these union symbols being square or round. There is no meaning there. I was just cutting and pasting. So if this is an open coloring, then one of the two alternatives applies. Alternative number one, there is an uncountable L0 homogeneous subset of X. So in this open color, we have an uncountable homogeneous set. Or alternative two, there are L1 homogeneous sets Xn for n in n, which cover X. So you see, this is very asymmetric axiom. What it tells us, you see, we have here X squared, and inside X squared, there is this open partition or open subset. So L0 is orange open set. So either you can find a subset of X here is Y, here is Y as well. so that if you look at all pairs from Y, they all belong to the orange part, to the open part. Or if you cannot find such uncountable set, then you can cover X by countably many sets, so that each one of those sets is L1 homogeneous, and their union covers X, right? So for each one of these sets, X1, X1, right, the square completely misses L. Now, these two alternatives exclude each other. Why? Well, if Y is uncountable, and if there are countably many xn's, then Y has to intersect one of the xn's in uncountable set. But it is clear that Y and xn cannot even have two elements in common, because if you have two distinct elements, if they are in Y, that pair should be in L0. If they are in one of the xn's, the pair should be in L1. Impossible. So two alternatives contradict each other, but more importantly, this axiom is consistent with FC. I'll go to that in a moment. What is extremely important here, and this is what distinguishes this axiom from other axioms called OCA considered earlier, is exactly this asymmetry. You see, it is a fairly weak consequence of OCA that if you have an open coloring of a separable metallizable space, then either you have uncountable L0 homogeneous set, or there is an uncountable L1 homogeneous set. Because if X is countable, you can just cover it by singletons. There is nothing to say. This is not interesting. If X is uncountable, if you cover it by countably many sets, one of them has to be uncountable. And that uncountable set, well, each one of these xn's is L1 homogeneous. So this is much, much stronger than the obvious Ramsayan statement. And it is also very important the way that colors have been chosen. You see, when you first see it, you may wonder, well, okay, so we get uncountable set in the open, which is homogeneous for the open color, or countably many homogeneous for the closed color. What if we swap? What if we ask for uncountable closed homogeneous? Or, well, that other axiom is inconsistent. It's simply false. And also, what is extremely important here is that you see, if xn squared is subset of L1, then if you take the closure of xn and you look at a pair in it, pair x prime, in here, then you have sequences in xn converging to x and converging to x prime. And now, because L1 is a closed color, this implies that this pair also belongs to L1. So in other words, if you have a homogeneous set in this closed color, we can take its topological closure and still keep homogeneity. So alternative way of stating option 2 of the axiom is that X can be covered by countably many closed sets, so that each one of them is L1 homogeneous. Before I go on, oops, sorry, I forgot to do something. Let me just, what was that? Do not disturb. Right, okay. Back. Sorry, I just lost the thread. I was saying something. Oh, yes, right. So you see here, now, if you're a trained set theorist, when you see separable metallizable space, you may say, okay, Polish space. Yeah, okay, sure, so it's complete. No, it's not complete. Actually, it is extremely important that X is just a separable metallizable space And interesting applications of OCA are the ones when X is not Borel, it's not projective, it's nothing. It's just some garbage produced by taking an arbitrary automorphism of Kalkin algebra or something like that. And actually, even more than that, if you just ask, well, so what if I just look at a definable version of OCA? What if I just ask that X is a Borel subset of a Polish space, or continuous image of Borel subset of a Polish space? Well, both of those are provable in ZFC. So OCA for Borel or analytic sets, continuous image of Borel sets, they're both theorems of ZFC, and even more, this uncountable homogeneous set, you can even choose a perfect set, closed set which is dense in itself in that case. So it's really, important point is that the axiom talks about arbitrary sets of points in an arbitrary Polish space. Okay, so now of course this would all be completely useless if it wasn't for this theorem that this axiom is relatively consistent with ZFC. So proof uses Cohen's method of forcing, and definitely this is not the place to go over it. But nevertheless, I just wanted to say a few words about it. So this axiom was formulated by Topology, who proved its consistency using previous work of Baumgartner, Abraham Rubin, Shalah, and so on. Now, this axiom is a consequence of the proper forcing axiom that I briefly mentioned last time. So if you are familiar with the proofs from PFA, proving OCA from there is really an exercise. I mean, the deep thing was formulating it. So proper forcing axiom easily implies OCA. Also, one can force OCA over any model of ZFC by a countable chain condition, finite support, forcing iteration of length Aleph2. One just needs a trick. You see, there is this reflection component in OCA that you need to handle arbitrary sets of reals. You see, X can be set of cardinality continuum, and your typical iteration of forcing does not handle such sets. So one needs some sort of a diamond, basically diamond on cofinality omega-1 ordinals below Aleph2 to capture everything and to do some pressing down to get OCA. But anyway, sorry. So this was, I mean, if you have no idea what I was saying, that's okay. Basically, all that we need is that OCA is relatively consistent with ZFC. So proving that ZFC plus OCAT implies whatever proves really that whatever is relatively consistent with ZFC. And that's all we need. And what I'll try to convince you today and in the next few classes is that this is a very useful axiom. And if you work in functional analysis in a subject that deals with objects which are basically sets of reals or sets of separable Banach spaces or whatever, that you may want to keep this in mind. It has many consequences, and very often it has opposite consequences from those of the continuum hypothesis, which is why we locate it right now. Okay, so here is briefly the plan. We'll prove two consequences of OCAT as a warm-up, but first I just want to take our time and see examples of relevant separable metric topologies. Just because I noticed that sometimes people get confused when you just define partition and say it's obviously open without saying what's topology, and topology may not be obvious. So basically there are a few tricks that one uses all the time. First, of course, the reals in any Polish space. So it's any separable C-star algebra with respect to norm topology, any Hilbert space, any Banach space, separable. And more importantly, any subset of any of those. Next, look at strong operator topology on B of H. So this is topology which is generated by a countable family of semi-norms, and you just basically list those semi-norms. Just fix a countable dense subset of the unit ball of the Hilbert space. So this is not some funny Hardy space. This is unit ball of the Hilbert space. So sorry about possible confusion. And just define distance between A and B to be this sum of 2 to minus n, A minus B Cn, 2 norm of that, right? So each one of these norms is bounded above by 2, I guess, and therefore you get a finite sum, and this metric generates a strong operator topology on the unit ball of B of H. It's important that B of H itself does not carry a natural Polish topology. So you need to stay in some closed bounded ball. Similarly, if you look at the weak operator topology on B of H, well, same story, except that you just have a different countable set of semi-norms. And now you can recycle this enumeration of a dense subset of the unit ball, but now you just have A minus B Cm dot product with Cn, absolute value of that, and again, add them
Can I ask a trivial
yes,
question? It's clear that you get a distance, but how do you show that it's separable?
Oh, well, it's separable. Compacts are dense. Well, you see, I mean, okay, so you give me your epsilon. So I claim that compact operators are dense. Actually, finite rank operators are dense. Now, if you give me your epsilon, I have all but finitely many of these are going to be less than epsilon, right?
Yes, okay.
So I just need to be close, and the sum of the other ones is going to be at most epsilon if I just go high enough, right?
Yes,
so all
okay.
that I need to do is to check that every finite thing can be approximated, but now a finite consistent. So just give me your operator A, and I just find n which is large. Now let's just look at strong operator topology because we have just one of these. So I just want essentially look at span, closed span of Cj for j less or equal than n. This is a finite dimensional subspace, right? And I just look at projection to that finite dimensional subspace, and just look at A times P. So P is this projection. Operator of finite rank. Now, okay, so there are still too many of those, but I can basically, if I fix a finite rank projection, and this is a separable. You just look at matrices which have
with rational coefficients.
So that's it. Or I can just say, compacts are dense, right? I just found a compact operator, which was within epsilon of your operator, and compact operators are even norm. So that's it. And similar story for this. Instead, you just have two indices to worry about. Yeah.
Okay, thanks.
Welcome. Okay. Any other questions? Right. So we'll need eventually these topologies, not today, definitely, but I just wanted to put everything here. Now, next one that we'll need probably on Monday, again, our old friend, unit circle to the nth power. It's all countable sequences for unit circle. Now, distance again, we just take maximum of 1 over n plus 1 of distances of un minus vn. So again, this is separable for the same reason that we just mentioned for strong operator topology. And this is just exactly what gives us a Tikhonov topology here. And there is nothing special about the unit circle here. If you have a uniformly bounded sequence of metric spaces, if their diameter is uniformly bounded, you just use exactly the same formula. If you have product of separable metric spaces with perhaps unbounded metrics, you just need a little trick first. For any metric space, there is equivalent metric such that your space has diameter 1 in that metric. Just take, redefine, take D prime is minimum of 1 and original metric D. That doesn't change topology, right? So only the small values of epsilon matter for that. It completely messes up the coarse structure of the space, but we don't care about that. But topology is the same. So basically, a product of countably many separable metric spaces is separable metric space. Okay. There is more, and here is one which is very popular among set theorists, and for a good reason, the bare space, n to the n. So this is all functions from natural numbers to natural numbers. Now, how do we visualize that? Well, you just think of your function. Natural numbers are going up this way. So, and this is just 3, such that every point has countably many successors, and your function, you just put a graph here. So functions are branches through this tree, right? We have tree which has the root, and then it's infinitely branching at every point, and branching just corresponds to different values for f of n. Now, if you have two functions f and g, if they differ, there is a first place at which they differ. And that first place is what I call delta here. It could be 0. If f is equal to g, then this is infinite. And the distance between f and g is 1 over delta of f of g plus 1. This is separable metallizable space. Why is it separable? Well, all sequences which are eventually 0 are dense. What are basic open sets? If you just give me some finite sequence here, and just look at all elements, all f's which start with that sequence, that is a basic open set. One feature of this metric, this non-Archimedean bit, is that the very strong form of triangle inequality holds. If you have f, g, and h, then distance from f to h is at most maximum of distances from f, g, and distance from g to h. Right, so triangle inequality becomes somewhat degenerate, but this is a very nice Polish space that is used a lot. We'll need a space which is really this bare space in disguise, and we just spent much of the last week studying it. It is this part n. Remember, part n, it is space of these partitions. So E is sequence of these ej, j less than j in n, and each ej is an interval. I called it n of j plus 1. I call it f of j plus 1 here, because I'll need to refer to this function. So this is function f e of j. F e of j is minimum of e of j. So you see, if you have a function in the bare space, if function has the property that f of j is less than f of j plus 1 for all j, right? So if you look at the strictly increasing functions in the bare space, then those functions are in one-to-one correspondence with our partitions. Because remember, we had partitions not of natural numbers, but partitions of a cofinite subset of natural numbers. So we are allowed to skip a few points. Otherwise, you would have to require that f of 0 is 0, which wouldn't be a big deal, but there is no reason. Right, so we just identify partitions with functions like these, and from this topology we get topology. So we'll be using this very soon. You can think what does basic open set look like, right? So basically, basic open set of some E, you just fix first finitely many of its intervals, and then just say, well, after that, I don't know what happens. But the first finitely many intervals are these, and that is basic open set. And finally, this is a trick which is used all the time. If you have separable metric spaces x and y, here is x on the x-axis, y is on the y-axis, and there is a function f from x to y. So here is the graph of f. Then we want to talk about x, to refine topology on x, but we refine it in a way that we identify x with this point x, f of x. So basically, we are identifying, we are lifting x to the graph of f and identifying it with a subset of x cross y. If both x and y are separable metric, then x cross y is separable metric, subspace of separable metric space is separable metric. So we are just using that. And we are basically getting closer to home right now. Exactly the reason why we need OCA is that it will be handed some horrible functions, and we'll try to get them to be continuous. And it's exactly this trick, but by using variations of this, we'll be able to prove that those functions are reasonably behaved to large sets, and eventually, produce continuous functions and unitaries and whatnot. Okay, so that was the story about this part. And finally, we come to our first application. These two applications, the first two applications I'm going to give are not going to be used in any relation to operator algebras, but they are easy statements that are good to know, and basically they serve as a warm-up for what comes later. Just one more bit of notation. If our set X has a natural linear ordering, think of X as real numbers, not just if reals have natural ordering, then if I write X, Y with this less than, so basically it stands for two things. It means, I mean unordered pair of elements of X, but also I'm emphasizing that they are listed in increasing order. X is less than Y. So it's just basically a little device that saves us some time and makes it possible to avoid mentioning too many cases when we define things. All right, so here is the first proposition, assume OCA. If X is an uncountable set of reals and G is a function from X to R, then there is an uncountable subset of X such that the restriction of G to Y is continuous. Once I had a conversation with someone, I think he was in complex analysis, a graduate student, it was a long time ago. And I just want to say this because some people get confused by this. You see, you can have a function that is discontinuous everywhere. Just look at characteristic function of the rational numbers, right? So it doesn't have a single point of continuity, but then you just remove those rational numbers and you get function that is identically zero on all the irrationals. So it is continuous at every point of the irrationals, right? So the restriction is continuous. So this is important that we know what we're talking about, right? So we move to a smaller yet uncountable subset such that restriction is continuous. Okay, so here it is. Now we are using this latest trick. So we define topology on X by identifying X in X with the pair XGX in X cross Y. So I could be partitioning graph of G, but it's just easier to partition pairs in X. And now we partition a pair of points X and X prime, and here I'm using that trick, right? So it's X is less than X prime if G of X is less than G of X prime, right? So there is a reasonable picture here, right? So X is less than X prime. Well, we want G of X to also be less than G of X prime. I hope that you can see which one is prime, right? So here are the points. So basically, 2 points, a pair, belongs to the 0 point if restriction of function to that pair is increasing. Now this is open. Why is it open? Well, because here I have open neighborhood of this, which is disjoint from open neighborhood of this, and no matter how I pick points in those, I get still 0. Still a pair of points such that the restriction of G to that is increasing. Now, just in case you're wondering, you see you can have point very close to X here, such that G of that point is maybe here, but that's why we refined the topology, right? So this point here does not belong to that open neighborhood. It misses this box here. Anyway, so this is open coloring, and let's just see what does it mean to be in L1. Pair X prime is in L1 if G of X is greater or equal than G of X prime. So this is the closed color. Now, what does OCA tell us? Okay, so let's here. Okay, so case number 1. There is Y subset of X such that cardinality of Y is at least Aleph1, right? I'm assuming axiom of choice, so this is what it means to be uncountable. And Y has the property that Y is L0 homogeneous. Okay, well, then G restricted to Y is increasing. Now, that doesn't mean that G is continuous on Y, but it can have at most countably many discontinuities, right? If you have a discontinuity, then it means that you're skipping an entire interval. That interval contains a rational point, so you can have at most countably many of those because function is increasing. So by the time you get to next discontinuity, you have a disjoint interval, and your rational is different, right? So G has at most countably many oops, sorry, I just managed to misspell discontinuities, and G restricted to Y minus Z is continuous for some Z which is countable. Okay, so in case 1, we get actually even a very function which is continuous for a very clear reason. Now, what is case 2? Well, we can cover X by union of xn's, and each of the xn's is subset of L1 for each n. Okay, now because X was assumed to be uncountable, here it is. If you cover uncountable set by countably many sets, at least one of them is uncountable. So there is n such that xn is uncountable. And now if you look at L1, what do we have about L1? Well, function is non-increasing. It's maybe not strictly decreasing, but it's non-increasing. So G restricted to xn is non-increasing. And again, just like for case 1, it has at most countably many discontinuities and so on. Hence, it has at most Aleph 0 discontinuities, and G restricted to xm minus Z is continuous for some z of cardinality L0. Okay, now you can see here that this completes the proof that I actually use this weak consequence of OCA that I mentioned was weak. All that I needed was uncountable homogeneous set in L0 or uncountable homogeneous set in L1. And now you can play with this and just see that actually statement is really stronger, that what you can really prove is that either you have your function can be, a graph of your function can be covered by countably many non-increasing functions, or there is an increasing function on an uncountable set, including and so on. But anyways, so this is basically a baby version of what we'll be doing later on. And this is also a good example of this magical aspect of OCA, that it turns arbitrary into definable. You see, we just started from some uncountable set of reals and some function from that set of reals into the reals, and we actually produced a nice set on which that function is continuous. All right, so here is a remark here, an exercise. Continuum hypothesis implies that that conclusion of this proposition fails. Namely, there is a function from set of all reals. You don't even have to take some uncountable set X to reals, such that restriction of G to Y is discontinuous for any uncountable Y. And that implies immediately that OCA and continuum hypothesis are incompatible. This is probably the easiest way to see that, although we'll see a few more. Basically, every consequence of OCA that we prove is going to need to contradict continuum hypothesis. I just want to give you a hint here. So I guess you've seen a sufficient number of CH proofs so far. You know what to do. You just enumerate some things in basically fix a well ordering of objects you want to avoid, such that all of them are listed and every proper initial segment is countable, and then just construct your function by recursion. Now, just question is, what are those objects? Well, clearly you want to enumerate all pairs Y and G, such that Y is uncountable set of reals and G is continuous function on it. But there is a problem here. There are just too many uncountable sets of reals. There are 2 to the continuum many of them. So how do you do that? Well, there is a theorem, I think it's called Lavrentiers Theorem, although now it's, I guess, by today's standards, it's an exercise, real analysis. If you have a set of reals, countable or uncountable, that doesn't matter. But if you have a set of reals and a real valued function on it which is continuous on that set, then you can extend it continuously on a G delta set which includes your set. And the G delta just means intersection of countably many open sets. And basically, the idea of the proof is play with epsilons and deltas. It's those G delta, I mean, intersection of countably many open sets really comes from taking smaller and smaller epsilons, which means that if you want to construct this, all that you need to do is enumerate all pairs YG so that Y is a G delta set. And now there are only continuum many Borel sets of reals. And there are only continuum many continuous functions, because you just fix a countable dense set and just look at what is function on that. It tells you everything. So there are only Aleph1 many relevant pairs to avoid once you know that the construction itself is trivial. Okay, so I'm rambling here, but I just have to say one more thing. You see, this exercise is different from what we did before with automorphisms of saturated models and whatnot. Before, at any given stage of our recursive construction, we could handle only countably many tasks. The algebra was countably saturated, or some poset was directed, every countable subset was bounded, or countability was important, which is why CH helped. Here it doesn't matter. Really, the theorem behind this exercise is just that in ZFC, there is a function from reals to reals such that restriction of G to Y is discontinuous for any set Y of cardinality continuum. And the proof is identical to the CH proof. And this is the right theorem there. Right, so even if OCA holds, you still have functions like this. All right. Okay, so it was our first application. Second application looks very similar. Here it is. Assume OCAT. Now, here we have uncountable sets of reals, X and Y. And claim is there is an uncountable X prime subset of X and an increasing function from X prime to Y. Right, so there are X and Y given somehow. So you can shrink X to X prime and find an increasing function from X prime to Y. Another way to say it is that you can shrink Y as well to Y prime in such a way that X prime with respect to the ordering is isomorphic, that X prime and Y prime are order isomorphic. Okay, so this also has a long history, but history is not completely relevant here. So I just emphasized nothing here is due to me. So I guess once I say that, I don't have to talk too much about names. Okay, so here is the proof. Now, we have sets X and Y, so we are partitioning pairs of pairs, right? So our space that we are partitioning is really X cross Y. So it's really pairs in X cross Y that we are partitioning. And how do we partition them? Well, pairs X, Y, X prime, Y prime, we put them in L0 if there are two possibilities. X is less than X prime and Y is less than Y prime. So the first possibility is this. Right, so here are the pairs. So this is possibility A, or possibility B is just the other way. Sorry, it's not the other way. It's actually, yeah, the same really. I don't want prime here. And here is Y prime and Y. Right, I cannot use that notation with less than in subscript because, well, it just doesn't really fit here. But basically, again, this is almost the same partition as before. I'm taking, except that now I don't have fixed function. I'm actually trying to find the function. So 2 points are in L0 if the function that passes through those two pairs is increasing. Again, this is open coloring. Right, so this is my set, and literally with the product topology, this is an open coloring. Right, I can find small enough open sets around here, so that whatever falls there is still ordered in the right direction. Now, if I have an uncountable L0 homogeneous subset Z of X cross Y, then we can define F as required. Actually, basically, Z is really the graph of F. Right, so being homogeneous, for every point X, there is at most one point Y such that pair X, Y belongs there. So, so the L0 homogeneous case is easy. Let me just see if I wrote something. Oh, yes. So we just need to prove that X cross Y cannot be covered by countable many L1 homogeneous sets. Right? If I prove this, then I'm done. OCA tells me that there is an uncountable L0 homogeneous set. So assume otherwise. So assume that X, that X cross Y can be covered by union of Zn's with the property that Zn squared is L1 for each n. All right. So what do we do now? Okay, so let's fix x in x. Now, you see, we are partitioning this entire square. Here is our little x. So you see this x cross y is subset of the union of z's. And now, okay, let me write now. So x, so these are my curly brackets. Sorry about my handwriting. This is subset of the union of z's. Now, since y is uncountable, at least one of the z's has to hit this set in an uncountable set. So let's call it n of x. Fix n of x such that x cross y, sorry, my little x and cross look the same. Let me know if you're having difficulties navigating. So that
maybe you should say that it's singleton x cross z then the union.
This was my singleton, yes.
No, above you have Zn is a subset of. Ah, no, you're right. Sorry.
I'm okay. Okay.
Yes.
Okay. Yeah, but thanks. I mean, it is good to make sure. If I confused you, then I probably confused everybody. So anyway, sorry. So anyway, so where are we? So we fix x such that this is uncountable. Now, what does that mean? Well, look, you have little x here, and you have some uncountable. Well, if you have an uncountable set, then it has at least 2 points, and so there is some rational inside here. So fix, let's call it p sub x in Q, such that p sub, okay, I'll use p sub x belongs to the convex closure. No, this is horrible notation. Let me just try to come up with a reasonable notation here, such that, okay, I'll just write it all, such that there are y and y prime with the following property: xy is in Zn x, xy prime is in Zn x, and y is less than px less than y prime. Right, so I was about to say that px belongs to convex closure, but I guess that would probably only be confusing. Okay, so we have, here is this n, and px is here. Okay, now how many possible parameters n of x and px we have? Well, only countably many. So there is an uncountable subset of x, which consists of elements that have the same parameters, right? So fix n p so that set of all x such that n of x is n and p sub x is p is uncountable. Let's call this x1. Okay. Now we should be done. So let's see. So x. Okay, I forgot the proof. Just a second. Okay, of course. So actually, let's just to see what I forgot, not only the proof, but I forgot what was the definition of L1. So we never actually said. So here is the definition of L0. Let's write what it means to belong to L1. So we have a pair of pairs, x, y, x prime, y prime, belongs to L1 if and only if A, x is less than x prime and y is greater or equal than y prime, or B, no, x, sorry, so what is the negation of this here? X is less than x prime and y is less than y prime, or, so what do I get if I negate this? I get that x is greater or equal than x prime, or y, I'm sorry, so you see this is again, I haven't been taking this proof. Okay, so let's see here what exactly is L1. L1. So if okay, so if not A and not B, not A is x is greater or equal than x prime, or y is greater or equal than y prime, and B is x is less or equal than x prime, or y is less or equal than y prime. Okay, let me just copy this here. All right. So now we can. So this should contradict one another. Let's see, what do we have? We have this uncountable set. Now we can assume this is uncountable set. Okay, we just need two elements of that set. Okay, so fix x less than x prime in x1. Now what do we have? Well, let's draw it. So here is x prime. So they are on the x side. Here is px, which is equal to px prime, right? And now what we know is that both x and x prime have elements on both sides of this. And let's see, so how do we, so again, x greater or equal than x prime. So in my case, x is greater or equal than x prime, or y. So I just need to choose points on the right sides of these. Okay, so let's.
I think you have to take the point above the px for above p for x and above and below p for x prime.
Okay,
and then you get
that's
an order
exactly what I
reversing
was.
function.
That's exactly what I wanted to figure out which one I wanted. Thank you, Mattel. So okay, so let's do it, right? So we have px prime is equal to px. So fix y greater than px, such that x y is in, I forgot what was that, the name was Zn, right? Zn of x. And x prime, y prime is also in the same Zn of x, right? So these two pairs, actually it's y is here, so sorry, this picture is become, oh, this was not, here is y, here is y prime, right? So here are my pairs, and this is decreasing function, and this here should be saying that function is not decreasing, I guess. Yeah, I guess I just, this should contradict this.
No, actually, I think I said the opposite. So you find an increasing function, and the coloring is saying that your function is not. So you should choose the other 2 points.
All right. Okay. So I'll just change this to prime. Thanks.
Sorry,
and I'll raise this
fault.
one. Okay. No. It's no. Thank you. It's good that you just made me look slightly less embarrassing. I'm sure it was on purpose. Thank you. Very nice of you. So I'll return it to one day. So I'll say something embarrassing in one of your talks. Okay. So here are the points. Right. So let me just change. Right. So y prime is greater than px and y is less than px. And now we have a decreasing function. And L0 was not supposed to be decreasing. So why do we? So here we have x is greater or equal than x prime. And y is less. No, x is less. No, okay, so this is false. You change your mind again?
No, the point is you have you redo what I said that was wrong. So I think you have to choose y below px and y prime above px, and you get that the pair xy x prime y prime is in L0, which is impossible because it's they are both in z and x, which is homogeneous for L1.
Yeah. Okay. Okay. So here actually let me put them in some other color. So here are points. Right, so this is an increasing function, and that was supposed to be exactly so it's supposed to be in L0, right? Actually, it is probably easier to look at it that way. So this pair, right? So this pair is clearly in L0. Yeah, thanks. So it's actually the whole business with looking at this is this. So right, thanks. So xy x prime y prime belongs to L0, which is contradiction because they both belong to L1 homogeneous set. Okay, so this was complete waste of time, this looking at negation. So I just need to check they're in L0. Okay, thanks. Okay, so this was the second application. Let's actually, I think it is on the next slide. What we just proved is that if you have two uncountable sets of reals, then they have uncountable subsets which are order isomorphic. And you can also replace increasing with decreasing. It's the same proof. And again, just like in the previous situation, continuum hypothesis implies there are uncountable subsets x and y of R, such that there is no uncountable x prime subset of x, and an increasing f from x prime to y, or a decreasing. She can do it at the same time for the same set. And again, proof is very similar to what we had a moment ago, except that now you're just diagonalizing over all functions. You're just choosing a set, not a function. And just like before, this has little to do with continuum hypothesis. You can just drop continuum hypothesis and replace uncountable with of cardinality 2 to all f0. And you get this. So just, yeah, okay. So this is a statement that has no relevance as far as I know to C-star algebras, but it shows to us some of the tricks used in when applying OCA. Okay, so now the next proof will take a while, and the next statement is something of direct relevance to what we are doing. As you can see here, you have this approximate sign. This is not proposition 9.957. Let me just tell you what 957 has a shorter statement. OCAT implies that B is equal to Aleph 2. B is this German fracture letter used to denote certain small cardinal associated to the continuum. I just need a specific instance of this, so we are just we're not even going to define D in this B or B or D in this course. All that we need to know is that for every family of partitions of natural numbers, which has cardinality Aleph1, it is bounded in that ordering that we defined before. And this is going to be a very, very important statement for us later on in the proof, because let me actually, instead of starting the proof, which makes no sense, this proof will take most of the next lecture. Well, half of the lecture for sure. Let me just say why is this important. Remember, when we used continuum hypothesis to construct an outer automorphism of the Calkin algebra, we picked this cofinal family of partitions of cardinality Aleph1. And an important point was that if E is less or equal star than F, then this space F of E was included in F of F plus the compacts. So if you have less or equal star increasing family of partitions, then you also have increasing family of subspaces. And by recursion, you define these automorphisms on those subspaces. We were able to survive on limit stages of countable cofinality to uniformize a sequence of unitaries by a single unitary. Now, this implication of consequence of OCA tells us that if we try to do that, if we try to construct an automorphism by recursion, by defining it on different F of E's, we will have to necessarily run into a situation in which at some point we have increasing uncountable family of partitions, and we need to uniformize all of them at the same time. Because every subset of cardinality Aleph1 is bounded. So the first time you hit an uncountable cofinality stage, you have to put something on top of it. And the proof that we used doesn't work, because if you remember, the point was that inverse limit of those groups, of countable family of groups, was trivial. That function was surjection, and you just diagonalize over countably many sequences, and because it's a sequence, you can just put them together. Like we were doing it several times, versions of this. So that's not going to work here, because you have to somehow uniformize Aleph1 of them at the same time, which is impossible. We'll see it in several different ways why that cannot be done. Let me just say, I'm not sure if I should start this at all. Basically, there are all sorts of things that we should do in order to get prepared, but maybe it's better if I just stop here. Oh yes, before I ask you about the questions, since again, it is reading week right now, some of you submitted homework, some haven't. So if Anyway, let me know if you need more time for homework. You see, one of the things was that nobody complained when I put due date to be at the end of the reading week. Unknowingly, I forgot about reading week. So I took that as a sign that nobody cares about reading week. If you care about reading week, well, even if you don't, yeah. Anyway, so I'm not going to grade anything. If you want, you can just have until Monday, say, or even, well, until, let's say until next Friday. Let's say you have an extra week for homeworks if you haven't submitted them yet. Yeah, if you submitted already, you can resubmit. That's fine. Right. Okay. And again, on Monday, I'll see if there are many people who complain. I may go over some of this once again quickly, but there is recording, so hopefully they'll at least look at the recording. All right. Any questions? Okay, I'll take it as a no. Okay, so great. So it's good to see you. Take care, and I'll see you on Monday. Yeah, so have a good weekend and be careful. Bye.